Um, we have our good friend Eugene Silberstein here from HVAC Excellence and the ESCO group. I think many of you will remember his very illuminating presentation last year on heat pumps. I'm sorry if my voice is giving way, but maybe that's a signal that I should just shut up. So, hey, go ahead, Eugene.
Thanks, Larry, and thanks for the opportunity to come back and present again. And it's neat that you did mention last year's presentation because I did get a lot of feedback from that, and I took the opportunity this year to elaborate a little bit more on some of the ideas and concepts that I brought up last year. So I think I got the award this year for the longest session title, Inverter Controlled Heat Pump Systems, Operation Challenges and Classroom Demos. And, being that we do have relatively limited time today, I did want to concentrate on some low-hanging fruit. I did want to touch briefly on some of the concepts and ideas that I introduced last year, but I also wanted to share with you as instructors some of the activities and ideas that I brought into my classrooms. We speak a lot about heat pumps, and our job is to train our incumbent and future workforce. And what I'm going to present with you today, to you today, is really just some ideas on how I go about teaching these concepts to my students. So for those of you who don't know who I am, my name is Eugene Silberstein. I've been in this industry forever. Presently the Director of Technical Education and Standards at the ESCO group, and I've written a couple of books on HVAC. Most of you on the attendance list I see that I already know. So for those of you who I don't know, hello, and we could circle back at any point. So we have a few discussion topics for this afternoon. Like I said, we do have relatively limited time, but again, I want to approach this from the educator standpoint and bringing this information easily to our students. So the discussion topic list is relatively brief. First, we want to start off with why heat pumps don't work and why people hate them. An easy way to teach inverters, how I teach transistors. I had touched on this last year, but I did get a lot of feedback wanting some more information on how I do that, some airflow challenges, and then a couple of exercises that I bring right into the classroom to keep the students engaged, to keep the students involved in the learning process. Now, with tongue in cheek, I started off saying why people hate heat pumps and why they don't work. Well, we love heat pumps and heat pumps do work. And one of my colleagues had mentioned all heat pumps are created equally and then they're installed. So we do have some challenges, right? Older generation heat pumps, we've been talking a lot about inverters over the last couple of days, but think back to our older generation heat pumps. We had single speed compressors, single capacity systems. They had two speeds. They were either full on or full off. So the system had frequent starts and stops. Energy consumption was a big deal because we had our end users who weren't used to heat pump systems and how they actually function. And to alleviate a lot of the nuisance service calls that our contractors were getting, they were inadvertently, of course, tying second stage heat, our electric supplemental heat, onto first stage. So whenever our heat pump called for heat, we were getting vapor compression heating as well as second stage electric heat. So some of the challenges that we're facing with heat pumps are improper system sizing, improper installation, improper charging, unrealistic expectations of what the heat pump system is going to do. Like Thomasina was mentioning before, talking about gas systems. Well, if you're operating a gas-fired furnace, your discharge temperatures are going to be a lot higher than they are with a heat pump. So when you have an end user who is used to fossil fuel heating systems and they feel the discharge air and it's not as hot, then the heat pump in their mind is not working correctly. There are a lot of airflow challenges, especially when we get into inverter controlled systems. If we have an inverter controlled blower, for example, chances are that blower is programmed to deliver constant volume. So if we have an undersized or an improperly sized air distribution system, we're going to face challenges with blower speed as the inverter ramps up to meet the required airflow needs. And then we're going to end up with noise issues. So a lot of this boils down to technician education. How are we training our people? How are we training our students to learn about heat pump technology? And if our students have a better grasp of heat pumps, how they work, what the expectations are of the end user, then once they get out of school, once they get their jobs, once they're dealing with the public, then they can better educate the end user and clearly communicate what the reasonable expectations are for heat pump systems. So again, just want to reiterate this. This is a slide this is an example that I use every time I talk about heat pumps. I am originally from New York, grew up on Long Island, and in the summer we properly sized and we designed air conditioning systems around a design outdoor temperature of 85 degrees. So with a design indoor temperature for cooling of 75, we're looking at a 10-degree delta T from inside to outside. So our heat pump system, when it's operating in cooling, and I'm talking about traditional single-speed heat pumps, when that heat pump system is operating in the cooling mode, we're really only moving heat against a 10-degree temperature difference. Now, if we look at that same system in the heating mode, we're designing a system at an outdoor temp of 15 degrees on Long Island and an indoor temp of 70 degrees. So we're asking a system to push heat against a 55-degree delta T. So if the system is not properly sized, if it's not properly installed, if it's not properly charged, if it doesn't have proper airflow, a heat pump system that's operating in the cooling mode might be able to satisfy the cooling needs of the space by simply running a little bit longer, and the house will be cool. Now, when we get into the cooler winter months, now we're asking that same system that wasn't properly sized, installed, charged with improper airflow, we're asking that system to push against 55 degrees. So any imperfections in system design, charging, airflow are going to become more obvious. And as we know, being really cold is a lot more uncomfortable than being a little warm. So having said that, we want to teach our students about how inverter controlled heat pumps function, how they work. And a lot of times when we're teaching relatively complicated subjects, our job as instructors is really to make it easy for our students to grasp the concepts and not give them a lot of extraneous information that they may or may not need at this time. Teaching psychrometrics, for example. One of the biggest mistakes I made when I started teaching psychrometrics was give my students the psychrometric chart on day one. Teaching pressure enthalpy, giving my students a pressure enthalpy chart on day one. If we start trying to teach inverter technology by giving our students something like this right at the beginning, they're going to run for the doors. So my suggestion is lock the doors before you do it. Yeah, this is a typical inverter. All right, so we are taking single phase AC power and converting it to artificial three-phase for our ECM motors, for example. But breaking things down into bite-sized pieces really makes the learning a lot easier. So I'm a big fan of breaking things down into bite-sized chunks for our students. And even this circuit, all right, it has an AC power supply, it has an output resistor, but it has 4 diodes in it. And at the level that I'm teaching my students, I try not to get into semiconductors and P material and N-type material and how a diode functions. And when I describe this to my students, I refer to a diode as a check valve for electric current. It allows current to flow in one direction and one direction only. And for the purpose of teaching how an inverter works, knowing that a diode is an electrical check valve is actually enough. So for example, during the first half of an AC signal, all right, we can trace out. We see the current flows starts in a clockwise path, and we talk about how current flows through diode 2, can't flow through diode 1 because it's facing in the wrong direction. And basically go through this in words of one syllable to get the concept through to the students. And then in the second part of the cycle, in the negative half of the input signal, we could see that the current flow through the output resistor is the same, and we rectify the circuit. All right, boom, challenge 1, because there are 3 processes in the whole concept. All right, talking about the next stage is the DC bus. It's the capacitors. All right, so what does the capacitor do? It's really taking that DC, that pulsating DC signal, and smoothing it. And when I talk to my students about it, I really talk to them about capacitors charging and discharging. And when that capacitor is discharging, the voltage that's realized at the output is greater than that of the input signal. So we end up with this relatively smooth DC pulse. And this is where it starts to get fun. So that DC signal that we've created from the input AC power is then transferred to a series of transistor pairs. Again, getting into the whole concept of transistors, not a fun concept. But what happens is, if we get too deep into NPNs and PNPs and MOSFETs and JFETs and bipolar junction transistors, it can really get confusing. And again, we're trying to convey the concept of inverters and how they work. So when I talk to my students about transistors, I really start the conversation with a general purpose relay. A general purpose relay has a coil, and a simple relay has a set of normally open contacts. Well, how does the relay function? Well, when we energize that coil, the contacts close and current flows through the circuit. And this is how my discussion of a transistor starts. It almost starts and ends right there. Again, just like teaching pressure enthalpy, handing out the pressure enthalpy chart, teaching psychrometric with the psychrometric chart, we want to teach concepts so our students can grasp them. If I'm teaching about transistor theory, I'm not going to throw my students a wiring diagram of an amplifier. I actually start my discussion of transistors with that general purpose relay concept, and then I move on with this 3/4 by 3/4 by 1/2 inch PVC T, right? And that T is altered. There is a spring-loaded wire inside. Okay, I'm actually going to hold it up here, and you can see that there's a wire blocking the path. And by putting pressure inside, I can either remove that wire or close. And the path, therefore, opens and closes. So, in that T is this pivoting wire that will either open or close a current path. So if that's closed, and I were to drop a ball, for example, into that T, it would not be able to pass. But now, what if I took and I exerted pressure? If I exerted pressure in the bull of that T, now I push that path open, and now if I were to drop a ball through the top, it will pass through. Well, that's the same basic concept of a transistor. But instead of physical force pushing to pivot that channel open, we're using electricity. So if we look at a basic transistor has a base, a collector, and emitter. And the collector-emitter junction, that path from the collector to the emitter, is that main path. Think of that as that normally open path, that normally open set of contacts on our general purpose relay. And think of the base as the coil. So as we apply voltage to the base, and again, this is very simplified, but it's sufficient for the general understanding of how this works for your students. As we apply voltage to the base of that transistor, we now open up that collector-emitter path for current to flow. And the way this works at the last part of our inverter, creating this artificial AC sine wave, we have the base on that first transistor opening. We energize the base, the coil of that transistor, and that transistor acts as an open circuit, and it starts to conduct. It turns on. And as you can see in that diagram, from 0 to 150 electrical degrees, that transistor is turning on, and then it is remaining on. And then at 150 electrical degrees, the base of that transistor is de-energized. And now that transistor turns off. And now you can see from 0 to 100, actually that's supposed to be 0 to 100 electrical degrees. We got 0 to 210. All right, that's my mistake. So from 0 to 180 degrees, we have a first half of an AC sine wave. And then for the second half of the signal, the base of that second transistor turns on and stays on, and then it turns off. So we now create this artificial AC sine wave. Now, when we talk about speed of a motor, the speed of a motor is governed by two factors of an AC motor. It's the frequency of the power supply and the number of poles that motor has. So now that we are creating this artificial AC sine wave, we can change the speed at which we energize and de-energize these bases, these coils, and that will increase or decrease the frequency of the motor. Now, for an ECM motor, we're using 3 transistor pairs. So we have here transistors 1 and 4. That's going to create 1 AC sine wave. Transistors 2 and 5, they're going to create a second AC power supply, and 3 and 6 another. So the first one is going to create an AC sine wave. The second one is going to create an AC sine wave. That's 120 electrical degrees out of phase with the first. And then we're going to create a third one. So although this does not accurately represent a 3-phase signal, what the motor sees is going to closely resemble a 3-phase power supply. So we have a set of instructions. We're going to energize the bases of different transistors at different times, and that is going to create this artificial 3-phase power supply. As we increase or decrease the speed, the time lapse in between all of these instructions, then the frequency of the motor is going to increase or decrease. As the frequency increases, the motor speed is going to increase. as that frequency drops, the speed of that motor is going to drop. Well, why is this important to us? Well, when we have ECM motors, blowers, that are feeding air through an air distribution system, that fan is going to ramp up if the duct system is undersized. Think about our duct system is smaller, more resistance to airflow. That blower is going to ramp up in speed to increase the speed of that motor to provide that constant airflow. So, having said that, what can we do in the classroom? We could talk about this stuff until we're blue in the face. But what I like to do in the classroom is I like to use these guys. All right. So this is called Kilowatt. This is a dynamite instrument. It's a pass-through device. So you actually plug it in, and then you can plug an appliance, a motor into this. That's obviously for 115 volts. This device will monitor the voltage, the current. It'll give you a display of the wattage, the active power. It'll give you the apparent power, the VA, the kilowatt hours consumed, the time elapsed, the frequency, power factor. You're going to get all of this right on the display by pushing the buttons. All right. So what I love using these for in the classroom is taking ECM motors that are not installed in air handlers, that are on the bench, that are installed in a blower, all right, and have them monitor the the criteria, the parameters at which this system is operating. So I just checked on Amazon. I used to be able to get these at Home Depot and Lowe's. They don't carry them anymore, but I did find them on Amazon yesterday. I did a search last night, and they're about $30. All right, but the learning that goes on with this thing is absolutely amazing. You could talk about power factor, you could talk about energy consumption, you could talk about kilowatt hours, and you can talk about calculations using power factor and apparent power and active power. But the students actually get to see this. So I just wanted to show you. I mean, those are available. And one other fun thing that I like to get is a decibel reader. It's a sound meter. Because as the air distribution system gets smaller and smaller and smaller, or is undersized, the amount of noise created by the blower increases. So what do we as HVAC techs do? What are we trying to teach our students? Well, we're trying to teach comfort. We're trying to teach how to heat, how to cool, but we're also trying to teach how to do it as effectively and efficiently as possible, and also do so at noise levels that are not excessively high. So I found those two on Amazon, which is actually pretty cool. So I just want to share with you a couple of things that I have my students do. So I take that ECM blower assembly with no ductwork, just the blower, and I have them obtain information, the voltage, current, the power factor, apparent power, all of these parameters, and also measure the sound level. All right, the meter that I showed you before measures sound levels between 30 and 130 decibels. Your target for an air handler should be about 20 decibels. Just for point of reference, normal conversation is typically between 40 and 60 decibels. A condensing unit, about 50 decibels. And once you get above 70, then that's when you could start to get damage to your ears. But I always have my students take a sound level reading of that blower. And then I have them calculate the cost of running that blower for 24 hours. And once they've done that, then I connect a 4-foot section of ductwork to that blower. And then they repeat those calculations. They take the readings, they do the calculations. How much money is it costing to run that blower for 24 hours? And they're also taking the reading of the noise level. And then finally, I have them do that with the 4 foot of ductwork, and then I have them block off half of the blower inlet. You can actually hear the motor ramp up, uh, you know, to very, very high speeds, but also the noise level goes up as well. And I have my students again grab that information and again calculate the cost of running that blower for 24 hours. Once they've done that, I gather the group back together and we start talking about the observations. So the bottom line, I just want to share this. Like I said, we just needed some low-hanging fruit. There's so many more ideas going on with this, but the purpose of my discussion today was really just to plant the seed. We can talk at the engineering level all we want about inverters, how they work, but the bottom line is we're out there to teach our students. Our students are getting introduced to the industry. They're entering the industry. So a lot of our air conditioning technicians are not going to become electrical engineers. They don't really need to understand, you know, the MOSFETs and the JFETs and the bipolar junction transistors and how the P material and the N material are layered together to create transistors. And again, it's great information. It really is great to know, but plant the seed and tell your students, well, this is how it works. If you're interested in a more in-depth discussion of how semiconductors function, then direct them to that content. But I've always found, you know, we're training people to go out and service air conditioning equipment to understand how it works, but we need to do so at a level that's gonna benefit them. So with that, like I said, a lot of low-hanging fruit. I wanted to touch on a few things. I wanted to expand on some ideas that you had asked me about. And you can reach me. My email is eugene@escogroup.org. My direct number, 224-248-9462. And I do want to thank you all for spending some time with me, for hanging out. I do want to thank the Best Center for giving me the opportunity to come back and chat with you. And if we have questions, I would be more than happy to address them.
Eugene, thank you once again for taking a complex set of ideas and, as you say, you know, breaking them down, using the power of analogy to convey the essence of the concept to the student, right? I think you're absolutely right. That's where it all begins. And if people then really want to get into the weeds and super nerdy, hey, go for it, right? But anyway, here we're really to compliment, right? You know, Robert says that you know, he loves your way of explaining the transistors, and then also kind of using the ECM with the kilowatt activity is also great. And Rob McNabb in Louisiana plans to use these activities
Awesome.
this coming semester, right? You know, I think again, you know, you also highlight the way that, you know, we use hands-on learning in a very visceral way to
Absolutely.
get people to retain information. Like again, you know, just I think you said that you could kind of shield about half the motor, right, and then hear it ramp up, right? And again, yeah, you know, kind of that added layer of visceral information is so important.
Absolutely. Thanks for that, Larry.
Yeah, yeah, you know, I think that you know, maybe we should follow up and consider doing a webinar with you, you know, on additional lesson plans, you know, on any host of topics, right?
Awesome. I'm all
Yeah.
for that.
All right.